Let's take this opportunity to bring in a special guest, Dr. Eric First, the principal investigator for the investigation known as InSpace 3, or investigating the structure of paramagnetic aggregates from colloidal emulsions. He's coming to us live from his lab at the University of Delaware. Welcome, Eric.
Thank you. Thanks.
Well, let's start off with a real simple question. What is this experiment you're working on?
Sure. The experiment is looking at fluids that we call magnetorheological fluids, and these are fluid materials that are composed of little tiny particles. They're about a micrometer in dimension, suspended in water. That micron, if you think about the dimension or the diameter of a human hair, that's about 1/100th the size of a human hair. And these particles, when they normally float around and the whole material behaves like a fluid, but when you apply a magnetic field to those samples, those little particles act like magnets, and they start to line up and they assemble with one another. And if you looked at this fluid, what we call the rheology of the material, how it flows, when you apply that field, it goes from a liquid to a solid very suddenly. And so we're investigating with these experiments some of the underlying phenomena, some of the details of how those particles come together and assemble into those structures, and how we can control that.
You know, right now we're looking at some recorded video of what we've affectionately dubbed the green blob here in Mission Control. And I know you know what this looks like because you've been watching the results of your experiment. Can you explain a little bit what we're looking at here?
Sure, absolutely. So it doesn't look like much, but it's actually pretty exciting for us. These are the black regions are the particles, and so those are the dimensions. There are several hundred microns. They're about the size of a human hair. So we're not seeing the individual particles, but what we're seeing is how they come together and aggregate in the presence of pulsed magnetic fields. The green that you're mentioning is just the light passing through our sample, so that's what allows us to distinguish the assembled structure from just the surrounding fluid. We monitor that structure. We look at how it evolves with time, especially as we toggle the field on and off, and we characterize the growth of those structures and how they develop. And that's giving us insight into not only the fluid properties of these materials, but giving us some sense of how tiny particles come together and do what we call self-assemble, or build greater structures from themselves.
So specifically, what kind of activities are going on with InSpace this week, and how does the crew help you set up the experiment?
Oh, I mean the experiments that we're doing, it's a number of our test run experiments. We have about 40 experiments that we run through to test a matrix of field strength, different conditions: field strength, field frequency, and suspension concentration. And actually, these particles are tiny particles that they're like little ellipsoids, or a little rice grain like particles in shape. If you were to look at them under a microscope, they would have that sort of shape to them. We have actually made a couple different types of particles that have different lengths, and so we're looking at experiments that ask, how does particle shape affect these processes as well? So the astronauts take our samples. I don't know if you have an image of those. I mean, it's a simple vial. The fluids disperse in that vial. They were sent up, I think, on, I want to say the Discovery, on the second to last launch, or maybe it was the Endeavour. About 2 years ago. They've been up there, and the astronauts take those samples. They integrate them into our experiment, which is in the Microgravity Sciences glove box, and it's roll film at that point. They set up the entire experiment, capture it on video. We get the downlink data. We monitor it in real time. And the key thing is that they record it on DV video, and that's sent back eventually, so that we can take that very high quality data and analyze it for our research results.
Okay, well, how does doing this experiment on the space station as opposed to on Earth make it possible?
Oh, well, these particles are heavy. And so if you were to do this experiment on the Earth, which we do experiments with these materials, but the limit is that they just fall out of suspension. So they'll rapidly, what we call sediment, right? So instead of being fluid and mobile and moving around, they just fall out. Now, we can do experiments, and it's sort of like 2D experiments, because they end up making sort of pancake-like structures on the bottom of our our sample vials, and we can look at that with microscopy. But the key with microgravity is, I eliminate that whole effect of having them sediment out. And so that makes the results that we have here much more generalizable in the sense that what we see and how particles assemble and the structures that they form, we feel that that can translate to particles of all different sizes. And what we're especially interested in is particles that are really small, nanoparticles, that we can't necessarily do experiments easily like this with anywhere. We're getting some insight into how nanoparticles assemble by doing these experiments. And from that, we're trying to figure out basically how we can take tiny particles and build bigger structures from that. That gets back to that kind of self-assembly idea that we're talking about. And we think that that's going to give us new technologies, new ways of manufacturing based on the idea of taking little building blocks, these little particles, and having them come together, self-assemble into bigger functional structures.
So, in a way, is this kind of like the old Star Trek Next Generation concept of nanobots?
Oh, I don't know. You'll have to fill me in on that. I can't remember the nanobot stuff. And, probably I dream of that. In some ways, the materials that we're trying to enable may seem more mundane. They may be thermal barriers. They may be materials that enable better utility of the solar power. Those. One of the things that we've learned in nanotechnology is how to build structures that are really tailored to transport light or to transport energy. The question that we have is, can we have those types of structures build themselves, basically, self-assemble? But they're not self-assembling in a sort of intelligent way, right? As a nanobot might, I guess, to form a bigger organism. It's a little less organized than that.
Okay. And these colloids, let's try to relate them to something that folks on the ground would recognize. Some things are like paint, where you have to stir it every so often to keep the paint particles into the liquid systems. Is that right?
That's right. I mean, and actually, the colloid sort of refers to a specific length scale of matter, and that goes back to the idea that these particles are on the order of about a micrometer. A colloid is usually it's a division of matter. It's a piece of matter that's anywhere from about 10 nanometers to several micrometers. So the micron range is a little bit larger size scale. Why that length scale is unique is that it confers on these particles the ability to move around by Brownian motion. All right, and that kind of gives the systems this ability to self-assemble. But if you go back to where people have seen colloids, you see it every day. Milk is a colloid, basically. It's a dispersion of fat droplets in water, and that's why it's so opaque. All those little droplets are scattering light, and clearly they don't sediment out or they don't cream, right? So they're moving around by Brownian motion in that fluid. Many of the consumer products that we use, and like you mentioned, paints and things like that, many foods have some aspect of being colloidal, and so it's a length scale of matter we use every day of our lives, but we often don't recognize that. And it's a really if you get into food and you get excited about those types of things, you'll find yourself actually working in this whole field of colloid science. And from there you can do many things. You can control how fluids flow. You can try to make these self-assembling structures. It's really quite exciting.
Well, how might you apply this for the benefit of folks on the Earth?
Well, like I said, the whole question of how we get particles to come together and sort of form structures, this idea of self-assembly, right? That's really what we really are trying to get insight into. And if you go back to the problem of fabricating nanomaterials or nanodevices, right? I mean, we know that we can make nanodevices like what we have today in microprocessors from this, sort of what we refer to as a top-down method, where we, add materials, we subtract materials, we build up the structure in a pretty laborious, batch operation with many, many steps. That's great. That gives us these functional devices that are super sophisticated. And those devices, those structures, they move charge around and they can do computations with that. What we're looking for is a method of manufacturing where where it would be scalable, where we could do large areas in a continuous process. So very fast, very rapid. You know, you're not going to make microprocessors with this, but you might make your new photovoltaic device out of it, or photovoltaic material, or your new thermal barrier, you know, for an application. I can imagine that would be a nice space application in some cases. So ultimately, this is really going to benefit people on Earth because it gives us this insight into making and fabricating new materials and essentially coming up with new manufacturing processes that harness nanotechnology.
Well, thanks. Hey, tell us a little bit about yourself. Where are you from? Where'd you go to school?
Well, I did my undergraduate degree at Carnegie Mellon, and that's not too far from where I grew up. I grew up in Johnstown, Pennsylvania, in western Pennsylvania, and I did my graduate work after being at Carnegie Mellon. I did my graduate work at Stanford University under under an advisor, Alice Gast, and after that, I did a postdoc in France, working a little bit in biophysics, so another area that's influenced by colloid science. And I've been here at the University of Delaware now for almost 12 years. My entire education's been in chemical engineering, but you can see that background really bridges all sorts of areas from the physical sciences to chemistry. So it's been a really rich and rewarding trajectory.
And how big is your team there at the University of Delaware?
I have about 7 PhD students. Sorry, that's not an approximate number. I actually have 7 PhD students and 2 postdocs working with me directly. Usually we have a couple undergraduates in the lab. And I have 1 or 2 high school students working with us as well. So it's a team of, you know, fluctuates between about 12 and 14 people, all different stages in their education, doing work in the lab and helping us out in all the experiments and all the discovery of knowledge that comes with that.
Well, Dr. Eric First from the University of Delaware, I want to thank you once again for being with us and explaining this very interesting experiment that has potential applications in so many areas of our lives. We really appreciate your being here today.
Thanks, Kelly. It was a real pleasure.